Okay, so this is the review session for EGME 417 for midterm 2 for spring 2022. Okay, so I looked at the poll online, and these were the topics that were the top. And so there was a tie. So I think everyone wants to see some time marching schemes. So we have a tie between explicit Euler and implicit Euler. I mean, those two kind of go together, and so it's good that we're covering both of them. And then the third one was diffusion with finite volumes. Okay, so I don't know if I'm gonna get to diffusion just because there's a lot to talk about with time marching, but we'll see how far we get. Okay, so let's go ahead and get started. All right, and so both explicit Euler and implicit Euler fall under the category of what we call time marching schemes for unsteady problems. Okay. The key word here is unsteady, and so whenever basically you have a time derivative in your equation, that counts as unsteadiness. Okay. And to look for that in your problems. So if you're given a problem on the exam and it has a time derivative, then it's most likely you're going to use a time marching scheme. And the problem will tell you too, because the problem will tell you whether you're going to use explicit Euler or implicit Euler. Okay. And so for example, if we look at our 1D case, okay, we had a situation that looks like this. Right, so here is our 1D unsteady convection diffusion equation. And of course, the man of the hour here, or the the term that we need to work with, is this one right here. Okay. And so the key to these problems is kind of to introduce a time index into our algebraic equations. Okay, because up to this point in the class, we've been doing finite difference methods, right? So we've been taking our derivatives here and replacing them with algebraic expressions, but we had only been doing that for a spatial term. Okay, and so the spatial term, remember, we always keep in the subscript, and so whenever we had a phi term right here, okay, in the denominator we had I comma j, I plus 1, all that, so on, right? The key here is to remember that this here represents our location in space, okay? Okay, but for unsteady problems, we also have to add an index for time, okay? And so that index goes in the kind of in the superscript here, okay? All right. And so these are the two things that we have to keep track of, right? And all of this is to reflect the fact that our phi here, our solution, is no longer just a function of space, but it's now a function of time as well, right? Okay. And so we have basically this situation going on where phi is a function of x being our spatial variable, and t, where t is our time variable. Okay, that's why you kind of see in our governing equation here that it's a partial differential equation, right? So we have partial derivatives and we don't have regular derivatives. And that has to do with the fact that our situation, our solution depends on multiple variables instead of just one. Okay. And so to solve these equations, or to write the computer code to solve these equations, we once again have to discretize it, right? And so we're going to have to rely on finite differences. But we have a difference here between what we do for the time derivatives versus the space ones. Okay, so the spatial derivatives, we've tackled those before, right? And so we're going to use finite difference for those. Okay. And so as an example, for our convection derivative here, we can just use our simple central difference. Right, so we have phi I plus 1 minus phi I minus 1, all divided by 2 delta x. Okay. And then for our time derivatives, we're going to use a simple forward difference, but we're going to do that forward difference in time instead of space. Okay. Okay. And so we have partial phi, partial t. Okay. For this class, we're not going to work on any situations with a multiple time derivative. It's always just going to be a first order one. And so that's all we have to worry about. Okay. Okay. Right. So when I say that we're taking the derivative in time, that means the index that we're incrementing up and down is going to be the time index, which is in the superscript. Okay. And so our time derivative here would be phi at I and time step n plus 1 minus phi at I and time step n, all divided by delta t. Okay. And so that's important. Right. And so what we can do from here is that, keeping this in mind, we should have everything we need to, form an algebraic equation. Remember, because that's always the goal with our finite difference, is to form this algebraic equation. Okay. All right, so let's go back up here and look at the governing equation. And so we have partial phi partial t plus u partial phi partial x equal k partial squared phi partial x squared plus our source term. Okay, so let's go ahead and plug in all of the appropriate difference terms for this. All right, so let's start with partial phi partial t, and we have that expression right up there. Okay. So that's our expression for partial phi partial t, right? Next, we're going to do the convection term. Right. I'm just assuming that we have a stable solution here. So I'm just going to use a just straight up central difference. Okay, then we have our diffusion terms. We have k, and our second order derivative, finite difference. And finally, we have our source term. So our source term is just q at xi. Okay. And so this is kind of our starting point right here. And so, traditionally what we can do is that we can multiply both sides by delta t. Okay. So we'll keep the delta x in the denominators here because it makes the expressions a bit more clean. Okay. And so if we multiply both sides by delta t, then we get phi I n plus 1 minus phi n plus. All right, I'm going to pull the two delta x out from the denominator, and so we have a u delta t divided by 2 delta x, okay, multiplied by phi plus 1 minus phi minus 1, okay, is equal to, again, I'm going to pull out the k delta x squared from this expression, okay, and we have our delta t. So we have k delta t divided by delta x squared, okay, phi plus 1 minus 2 phi plus phi minus 1, okay, plus q of x, q of xi multiplied by delta t, okay? Okay, and so the way these time marching schemes work, the idea is kind of the same for both, right? And so what we have right here is an algebraic equation, right? So we've accomplished our goal of replacing our derivatives with algebra, okay? Now the goal here is to rearrange this into a certain form, okay? And the way that we always want to rearrange it is that we want to put phi any n plus 1 terms on the left and any n terms on the right, okay? Okay. And so at this point, it's good to review. It would be good to review what those actually mean, right? So what do I mean by n plus 1? What do I mean by n, right? And so we know that the n here represents our time index, okay? But the difference between n and n plus 1 is actually very important, right? And so let's start with n. And so any phi term that's marked with an n, any of our solutions marked with an n, this represents the solution at the current time step, okay? You can think of this as the solution in the present moment, okay? Okay. Right. The important thing to know is that if it's already happened, right? If it's in the solution in the current moment, then this is something that we know. Okay. Okay. And if it's known, then we can move it over to the right-hand side of the equation. Okay. Right. So that's time step n. Next, we have time step n plus 1. Right. Time step n plus 1 here represents the solution at the next time step. Okay. Or in other words, you could think of this as like one step in the future. Okay. Right. And since it's happening in the future, it hasn't happened yet. And so this is something that's unknown. It's unknown, but it's what we want to solve for using our time marching scheme. Okay. All right, and so with that in mind, and if we count the fact that our source term here is also a known quantity, okay, then what we can do is we can rearrange this this equation into, you know, everything on one side we can say is unknowns, and everything on the right are the knowns. Okay? And so we basically want to set up an equation that looks like this, right? And so what we say is that the solution, our solution phi in the future, you know, one step in the future, it's going to be a function of what's happening in the present. Okay. Okay. And so in other words, you know, depending on where you are in the present, that's going to affect where you are, you know, like immediately just, you know, half a second from now, right? Think about, you know, where you're sitting right now. So you're sitting, you maybe you're in the library, maybe you're in your room watching this review video, right? And so what you do half a second from now depends very strongly of where you are right now, right? Like you can't just all of a sudden appear in Cabo or Cancun, right? Half a second from now, you know, because you're not there, right? You're watching this video and you know, studying for an exam. And so, you know, every action that you take or everything that happens to someone, you know, in the immediate future, right? And when I'm talking immediate, I'm talking about just like a matter of seconds. You know, it depends very strongly on where they are in the present, right? And so you can't make sudden changes to your, you know, to your situation unless you have superpower teleporting or something like that. Okay, but you know, to the best of our knowledge, that does not exist in real life, right? And so where you are right now, that's going to have a strong influence of what you're going to do, you know, half a second, 1 second, you know, 1 minute from now. Okay, and so it's the same thing with mathematics as well. Okay, and so what we say is that, you know, our solution at the next time step is a function of the known one. All that's great. Okay. But, you know, we only have a few terms here that have our time index, right? So if we look at our equation right here, the only terms here that have the time index n are these ones right here, okay? And so we could say right away that this phi I n plus 1, that's going to end up on the left-hand side of the equation, okay? Whereas this one, the one that just has a time step n, is going to end up on the right-hand side, okay? We already know the source term, and so the source term is known, so we don't have to worry about that, okay? But we have all the other phi terms that we have to worry about, right? So we have all these phi I, and I plus 1, I minus 1, right? We basically have these 5 guys right here, okay? And right now, you know, we don't really know what to do with them because they haven't been assigned a time index yet, okay? And so the question is, you know, what is the proper time index to specify for these quantities? Well, you know, it depends, and so you can you know, and so you can change it up, you know, depending on, you know, what kind of method that you want. Okay, and in fact, you know, what you assign for these quantities, what you assign for these phi values, that's going to determine which time marching scheme that you're going to use. Okay. Okay. And so we need to assign a time index, and we can either assign n or n plus 1. Okay, and depending on what you assign, you know, you can have one method or the other one. Okay, And so those are the two methods that we know, right? And so the first method, are explicit Euler. Okay. The explicit Euler has a time step of n assigned to it. Okay. Right, so all the phi terms that don't have a time index, we're going to assign n. Okay. And what's important about this is that we're going to, after we assign n, we're going to move them all to the right-hand side of the equation. Okay. All right, number 2. And so the other option, of course, is assigning n plus 1, and this constitutes our implicit Euler equation. Okay. Right, so for implicit Euler, we assign all the spatial derivative phis to a time index of n plus 1. And since those are going to be unknowns now, we're going to move them to the left-hand side of the equation. Okay. And so those are our two options. Okay. And so let's go ahead and take this equation here. Okay, let me go ahead and clean this up a little bit. Okay. And let me try out this feature. So let me go ahead and lasso select. Okay. And so let's take this and let's move it down. Okay. So here's our equation, and let's see what it looks like when we apply the explicit Euler and implicit Euler. Right. So let's start with explicit Euler because that one's just the first one that's listed. Okay. All right. So for all of these phi terms, I'm going to assign a time index of n. Okay. And since those are known quantities now, we're going to move them to the right-hand side of the equal sign. Okay. Okay. And so let's go ahead and work on that. And so we have phi I n plus 1 minus phi I at n. Okay. Everything here, we're going to move to the other side. And so I'm going to put an equal sign here. It'll be u delta t divided by 2 delta x. Okay. We're going to subtract both of these two terms. And so when you subtract them, their signs are going to invert. And so we have a phi I minus 1 at n minus phi I plus 1 at n. Okay. Right. All the diffusion terms, we're going to keep it on that side because they're already where they need to be. Okay. And then we're going to add our source term now too. So delta t q of x I. Okay. Okay. So all that's great. We need to move this one over to the right hand side too. Right. I kind of forgot him. And so let's go ahead and do that. And let's rearrange the right hand side so that we sort them by the common factors of phi. Okay. Okay. Okay, so on the left-hand side, the only term that we have there is just phi I n plus 1. Okay. And on the right-hand side, we have all of our expressions here. Okay. All right. So let's start with the coefficient for phi I minus 1. And so this is going to be u delta t divided by 2 delta x minus delta t divided by delta x squared. Phi I minus 1 at n. Okay. Next, I'm going to write out the coefficient for phi I. Right. So first thing we have here is a 1 because the 1 is coming from the left-hand side. Then we have a minus 2 k delta t divided by delta x squared. This is phi I at n, okay? And to this, we're going to add our phi I plus 1 n term, okay? And so this is going to be a minus u delta t divided by 2 delta x minus k delta t, or excuse me, plus, as a plus. It's a plus up there too, okay? Plus k delta t delta x squared phi I plus 1 at n, okay? Then of course we have our source term q at xi delta t. Okay. And so this is our explicit Euler time marching equation for this equation. Okay. 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 And so here we have, obviously, we have an algebraic equation, right? And we can just go ahead and plug in directly all of these parameters, right? So we have the convection velocity, we have the diffusion coefficient, we have the grid spacing, as well as all of the time step sizes. Okay, so the time step size is delta t, right? So most of the time, those things are going to be given to you in the problem, and in order to apply this equation, you can just plug into this expression in order to get the time marching formula. Okay, but this process that we just went through, right? So taking our original equation, replacing it with the finite difference approximations, and solving for the appropriate variables, okay? And applying our time marching scheme, you should know how to do this on the exam. So this is an important part of this unit. Okay. Okay. It's not that difficult of a derivation, it's kind of building off everything we've done up to this point, but it's important to know. Okay. All right, so let me do a quick example. Let me just go ahead and repeat the in-class example, because I want to show you how to actually apply this in practice. Okay, so after that, then we'll review implicit Euler, and then we'll move on to diffusion finite volumes if we have the time. Okay. And so in this example here, let's take the case of an unsteady diffusion equation. Okay. And so for this unsteady diffusion equation, let's scroll up a bit. Okay. Then we have simply partial phi partial t is equal to 3 partial squared phi partial x squared. Okay. Okay. And so from this equation, we have no convection, and so we just have diffusion, right? And so if we assume, okay, if we assume delta t, the time step size, which is given to us, is going to be 0.1 seconds, okay? And delta x here, we'll assume it to be 0.25, right? Just for the sake of this problem. Okay. And from this problem, we can also see that u is equal to 0 because we have no convection, and k here is equal to 3. Okay. Okay, so let's go ahead and plug in the variables here, right? And so if we plug in the variables, if phi n plus 1 is equal to 4.8, phi minus 1 at n minus 8.6, phi at n plus 4.8 vi plus 1 at n. Okay. Okay. And so here is our time marching scheme right here. Okay, so this formula can be directly applied. And so what we're going to do is we're going to apply this at each of the nodes in our grid. Okay, because remember, we haven't learned how to do unsteady problems with finite volumes yet. But for finite differences, even though we're unsteady here, the idea is the same. And so for every node that we have in our grid, we should get an algebraic equation that explains how it evolves with time. Okay. Right, and that equation that explains this time evolution is going to be given by this equation up here, okay? Or you're going to have a boundary condition applied on that node, okay? Okay. All right, so let's go ahead and apply this, and let's assume that we have the following 5-node grid. Okay, so this is node 1, 2, 3, 4, 5. Okay. And so if we have 5 nodes here, that means we should have 5 equations. Okay. Right. And so since this is a 1D case, I'm going to neglect nodes 1 and 5, okay, just for the sake of time, because we know that those are on the boundaries, and so we're going to apply boundary conditions there. And so let me write out the equations for nodes 2, 3, and 4. Okay, and all it is just we're going to be applying this time marching formula up here. Right? So we start with node 2, and so for node 2 we have phi2 at n plus 1 is equal to 4.8. Phi minus 1, so I minus 1 is 1, okay, minus 8.6, Phi2 at n, okay, plus 4.8, Phi plus 1, I plus 1 here is 3, okay, and that's going to be evaluated at time step n, right? And we're going to do the same for I is equal to 3 and I is equal to 4 as well. Okay, and so those are our first 3 equations. Okay, next we have the equations for the boundary conditions. Okay, of which I didn't give you, but that's okay. Let me fix. We'll modify this problem a little bit because I do want to go over how to handle situations when you have time, okay, or a time variable in your boundary conditions, and so. Okay, and so for this one, we're going to assume that phi at x is equal to 0. Okay, so this is going to be phi1 is equal to, we'll say this is equal to 5t. Okay, and so that boundary condition is going to vary with time. Okay, our other boundary condition. Okay, so this is going to be on the right-hand side of the domain. So this is going to be at x equal to 1. We'll keep this one the same. So we'll see this is equal to 2. Okay. Okay, so now let's apply these boundary conditions to get our last 2 equations. All right, and so for I is equal to 1, we have our Dirichlet boundary here. And so our Dirichlet boundary, remember in finite differences, we say this is equal to phi 1, okay? First node in our grid. And this is going to be equal to 5t, okay? But, whenever you have a time index or time variable like this, you have to evaluate it at a certain time, right? And so that's going to be t sub n. Okay, so t sub n, this is the current time. Okay. And so whenever you're running unsteady problems like this, there's always the, I would say, unspoken assumption that you start at t is equal to 0. Okay. Okay. And so as time goes on, as you kind of solve for time step on time step, the time is going to advance, right? And each time step, the assumption is that each time step, the time is going to advance by the time step size, okay? And so for the first time step, t is going to be equal to 0. For the second time step, t is going to equal to 0.1 because that's the time step size. And for the next time step, t is going to equal to 0.1 plus 0.1, which is 0.2, and then so on and so forth. Okay. All right, we'll do an example of and we'll take this all the way to the point where we can advance in time. Okay, so that's the first boundary condition. Next, we're going to apply the boundary condition on the other side. Okay, so we have phi d phi dx is equal to 2, so we have our Neumann boundary condition. And so since we have a spatial derivative here, we're going to use a spatial finite difference. Right, so we're going to apply our forward difference. So we said that phi 5 minus phi 4 all divided by delta x is equal to 2. Okay. Right, but just like the issue that we saw before with the with our original equation, we have to assign time indices to these phi values. Okay, I guess up here too. Okay. And so the key here is that in order to form our explicit Euler, we need to have at least one n+1 term, right? And so and to be more specific, we need an n+1 term on phi 5. Okay? Okay. And so this automatically will go just like that. Okay. But we're a little bit restricted here because with explicit Euler, we only have room for one n+1 term per equation. Okay. Okay. And so that kind of forces our hand, and it makes it so that the other term, we have to evaluate it at time step n. Okay. All right, and so if we solve for phi 5 here, and so we say phi 5 at n+1 is equal to 2 delta x plus phi 4 at n. Okay. And so this is our fifth equation. Okay. Right, and so now we have all 5 equations here. And so let's go ahead and put this in matrix form, right? And explicit Euler has a very interesting matrix form. Okay. And so explicit Euler has the following structures. We have phi I n+1 is equal to, we have a coefficient matrix multiplied by phi I at n. Okay. And to this, we're going to add an additional vector here, b, to include any extra terms, any of the boundary conditions, or if we have source terms, that's usually where they go. Okay. Great. And so we have phi I n+1 on the left, because each equation only has a single n+1. Okay, so we can afford to keep that over there. Okay. But what you should notice in this equation is that normally for these problems, the coefficient matrix is actually on the left-hand side, right? That's where it usually is for all of our steady state problems, and actually for implicit Euler, it's over there too. And so in order to solve for the solution, we would have to invert A, right? And so we'd have to take the inverse of A and multiply the other side. Or in other words, what we call that is, we solve a linear system of equations, okay? Here we don't have that. Here the A matrix, the coefficient matrix, is already on the right-hand side of the equation. And what we want to solve for is on the left, kind of by itself, okay? And so what we can say, and this is a characteristic of all explicit methods, is that in order to solve this system in time, all we need to do is just perform matrix vector multiplication, okay? And the thing about matrix vector multiplication is that it's really, really fast. Okay. At least compared to solving a linear system of equations. And so this occurs, very, very quickly. Okay. And so with that in mind, let's go ahead and form our linear system here. Okay. Or our matrix form, I'm sorry. Okay. And so on the left-hand side, we have all the phi i's. Okay. Right. And on the right-hand side, we have the following. So we have 0. Let me build this column by column: 4.8, 0, 0, 0. And we have 0, minus 8.6, 4.8, 0, 0, 0, 4.8, minus 8.6, 4.8, 0. Okay. We have 0, 0, 4.8, minus 8.6, 4.8. Okay. This last column here, excuse me, sorry, we don't have a 4.8 there. This is the last row. So this is just a 1. Okay. And we have 0, 0, 0, 0, 4.8, and 0. Right. And so this is multiplied by all the phi i's. Okay. Plus we have our extra terms here. And so we have our Dirichlet boundary condition, which is 5Tn. All the interior nodes don't have anything because there's no source. And then the right here, we have 2 times delta x, but delta x is 0.25. And so 2 times that is going to be 0.5. Okay. Okay, so that's our linear system. Okay, or not our linear system, our matrix set of a matrix, matrix equation. Okay. Okay. And so this basically gives us the recipe on which we can advance the system forward in time. Okay. And so if I ask you to advance a system like this forward in time, you would basically take this matrix system and carry out the arithmetic. Okay. Okay. Of course, we have to start somewhere, and so we have to start with an initial condition. Okay. And so you just have to perform the matrix vector multiplication. Okay. Okay, and so one of the more common initial conditions that you can see is what's called a zero initial condition. And so what we assume is that the initial values for all the fees are going to be zero. And so in other words, all the fee values, all the fee n's, those are going to be zero. Okay. All right. So let me go ahead and advance this forward. I'll do it 2 times. I'll do advance twice, so you can see what it looks like. Okay. Okay. And so after one step, our solution is going to look like this. And so I'm not going to write out all the fees, but these are all the fee n plus 1s. Okay. Here we have the A matrix. Okay. These are all coefficients. Okay. Here we plug in the initial conditions. And so our initial conditions are going to be all of this. Okay. Okay. And then to that, we're going to add our extra vector here. Okay. So first thing we have is 5 times Tn, right? And so Tn at this step, okay, right? So we've advanced forward 1 step in time. And so Tn here will be the initial time 0 plus delta t, okay? And so it's going to be 0.1. And so this first entry here is going to be 5 times Tn. And so Tn is going to be 0.1. Okay. And the bottom here is 0.5. Okay. And so since this is, since all this is 0, and so all this is going to cancel out right here. Okay. And so what we get after 1 time step is phi 1, phi 2, phi 3, phi 4, phi 5, and plus 1 is equal to 0.5, 0, 0, 0, 0.5. Okay, so that's what we get after this time step. Okay. Okay. After 2 time steps, we're going to advance this forward 1 more time. Okay. And so at this point, it's important to note, what the what the t value is. Okay. And so here we have Tn is equal to whatever the previous t was. So the previous Tn was 0.1. Okay. And to this, we're going to add another delta t. And so this is going to be 0.2. Okay. All right. And so let's go ahead and form our matrix system. So we have phi n plus 1 is equal to a. Okay. Now, instead of all zeros here, we're going to plug in the solution from the last time step. Okay. Okay. And so we have 0.5, 0, 0, 0, 0.5. Okay. And to this, we're going to add our extra vector here. Okay. So our extra vector, first we have 5 times Tn. So we have 5 times the current time step, the current time, which is 0.2. Okay. We have 0.5 at the bottom. Okay. Okay, so I'm not going to carry this out, because it's just a bit busy work, because I do want to get to implicit Euler. I want to talk about that for the last 10 minutes. But this kind of gives you an idea about how to actually carry out this time marching. Okay. One other thing that I'll note, that's important to know is this notion of steady state or not. Okay. And so, we've introduced these schemes for time marching, right? But the situation is actually only going to change with time if one of the parameters change with time, right? So maybe perhaps, I was a little bit bullish at the beginning. I said that if you have the time derivative partial phi partial t, then you have an unsteady situation, right? So that's not necessarily true. And so, you can solve a problem as unsteady, right? You can solve a problem as unsteady just fine. But whether that situation is actually going to change with time depends on the parameters of the problem, okay? And, if you have a situation where you have t in either your boundary conditions or in your parameters, right? So either your diffusion coefficient or your convection velocity, if t appears in one of those, then your situation is still going to continue to vary in time. Okay? Or in other words, it's not going to reach steady state. Okay? And so in this problem, we do have one such boundary condition. Okay. And so we have this boundary condition here, which says that phi at x is equal to 0 is equal to 5t. Okay. So this tells us that as time goes on, this boundary condition is going to keep climbing. Okay. Okay. So that's going to keep increasing. And so if that's going to keep increasing, then then we're not going to reach steady state, right? Steady state implies that, as time goes on, then things are not going to change, okay? And so that can only be true if your situation does not have any time in any of its parameters, okay? Okay, and so that's explicit Euler, and and we did an example for that. Let me very quickly go over implicit Euler for the last 10 minutes that we have. Okay. And so remember, the difference between explicit Euler and implicit Euler is whatever time index that we assign for the spatial derivatives. Okay? And so for implicit Euler, we're going to assign a time index of n+1 to all the spatial derivatives. And let me do this for 2D actually, just so that you can, just so you can see how it all works out. Okay? And so in 2D, our full equation looks like the following. So partial phi partial t plus u partial phi partial x plus v partial phi partial y, okay, is equal to k partial squared phi partial x squared plus partial squared phi partial y squared, okay, plus q of x and y, right? And so just like before, we're going to, replace everything here with the finite difference. Okay. And since we're in 2D, we're going to have two spatial indices now. So we have both I and j. Okay. And so first we start with a time derivative. And so that's going to be phi I comma j n plus 1 minus phi I comma j n. Okay. Next, we have the convection term. So we have u. And I'm going to assume a central difference as well. Okay, so central difference can be phi I plus 1 minus phi I minus 1. Okay. Both of these are going to be assigned a time index of n plus 1 now. Okay. Okay, so I plus 1 comma j, I minus 1 comma j. Forgot the y index. Okay. Then we have the y derivative, and so we have phi I comma j plus 1 minus phi I comma j minus 1, both evaluated at time step n plus 1. Okay. Right. And so this is going to be equal to our diffusion term. Okay, so we have k multiplied by
We have the second order derivative in x, since we have phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j. All evaluated at n plus 1. Okay. Okay, then we have the y derivative term. Okay. And then of course we have our source term. Okay. So we have plus q at xi yj. Okay. And we haven't multiplied by delta t yet. Okay. Okay, and so and so we can go ahead and work through the math here, and so it's a lot of algebra at this point. Okay, but when we work through the algebra, we're going to have a lot more n plus 1 terms here than we did before. Okay. And so in the end, you're going to have a system that actually looks like this. Okay, that's going to be different than our explicit Euler. So we have a phi I comma j n plus 1 is equal to phi I comma j at n plus b. Okay. Okay. And so now our coefficient matrix is on the left. Okay. And so remember, just like I mentioned before, that when our coefficient matrix is on the left-hand side of our equation, in order to solve for what we want, which is this guy, okay, we're going to have to invert that matrix. Okay. In other words, we have to solve a linear system of equations. Right? Okay. And as we discussed before, this process is a lot slower. Okay. Okay. And so the question is, why would you go through the trouble of doing implicit Euler, if it's going to be a lot slower than explicit? Well, and this is one thing that I've kind of forgotten to talk about up until this point, right? Whenever you have an unsteady problem like this, you're going to run into problems of stability, right? Specifically, if you're running explicit Euler and your time step size is not small enough, then your solution might become unstable. Okay, but if you're using the implicit Euler, then your solution is guaranteed to be stable. Okay, and that's a huge benefit under, especially if you're solving a very complex problem where, maybe the velocities are changing with time, then, a lot of times you just want to be safe and run a, run a stable time marching scheme, without having to risk it. Okay. And so on the flip side, okay, on the flip side, in order for explicit Euler to be stable, the time step size has to be small enough. Okay. Generally speaking, you're going to want to have a smaller time step size in general. but that's because of accuracy considerations, right? So it's not only stability that depends on the time step size, but also the accuracy, right? And so if you want to have a higher accuracy, you can have a lower time step size. But for explicit Euler, there's kind of a cutoff, and so you have to be below this threshold to even get a solution that makes sense. Okay. For implicit Euler, you can get away with a higher time step size. Your solution might not be accurate, but at least it'll be stable. And a stable solution, a stable inaccurate solution, is oftentimes a lot more useful than an unstable solution. Okay, so stability is very highly coveted, and so that's a good indication for, or that's a good feature for this. Okay. Okay. Let me go ahead and write out the final expression here just to kind of close it out, and then we'll wrap up the review session. Okay. And so if you go ahead and perform all the rearranging in algebra, you end up with the following for a 2D implicit Euler time marching scheme. Okay. All right. So first we have minus u delta t divided by 2 delta x minus k delta t divided by delta x squared. Okay. So this is phi I minus 1 comma j at n plus 1. Okay. Plus a positive u delta t divided by 2 delta x minus k delta t divided by delta x squared. Okay. And this is phi I plus 1 comma j n plus 1. Okay. Plus minus v delta t divided by 2 delta y minus k delta t delta y squared. Okay. Phi I j minus 1 n plus 1. Okay. Okay, then we have the phi I j plus 1 term. Okay. And then we have the phi I comma j term, right? So it's a lot of terms, right? So it's definitely not for the faint of heart. But a lot of these terms are only comprised of the same few parameters. And so you have the convection velocities, you have the diffusion coefficients, you have the time step size, and the grid spacings, okay? So it's just kind of different combinations of all of those parameters. Okay, so that's the coefficient for phi I comma j. And on the right-hand side of this equation, we have phi I comma j at n plus q at I comma j, okay, multiplied by delta t. Okay, so don't forget the delta t there. Okay, and so that is your implicit Euler equation for 2D convection diffusion using finite differences. Okay. Okay, so we didn't get a chance to get to finite volumes. Finite volumes is the most recent thing that we did, and so hopefully that's still kind of fresh in everyone's mind. Okay, but this was a pretty good comprehensive review of what you need to know in terms of time marching schemes. Okay. All right, so hopefully this was useful to you guys. Our midterm is not going to be until the 25th. Okay. And so I'm recording this video now just because I already kind of blocked out time for it in my schedule. But the midterm is not going to be until the 25th, and so that's still about 10 days from now. Okay. All right. So best of luck studying, everyone. If you have any questions about anything, as always, you can go ahead and reach out to me. And I will see you. I'll see you guys on Monday.